Hello everyone, welcome to my channel. In this video, we'll solve important J-Mains previous year questions from the chapter of work power energy. So this would be part 1 of the series in which I cover all the important previous year questions of work power energy, which have appeared in the mains and advanced examinations. So with that, let's move on to the first problem of the day. So we have a person who's pushing a box on a rough horizontal platform. He applies a force of 200 Newton over a distance of 15 meters. Thereafter, he gets progressively tired and his applied force reduces linearly with distance to 100 Newton. So the total distance through which the box has been moved is 30 meters. What is the work done by the person during the total movement of the box? So clearly in this problem, if you observe from this sentence to this sentence, what they have given us is how the force is varying with the distance. So the best method here is to draw an fx curve, right? So if I draw force versus displacement curve, initially it's given that for 15 meters the force was constant and it was equal to 200 Newton, and thereafter it's given that it decreases linearly with distance and becomes 100 newtons. So let's say and the total distance is given to be 30 meters. So this would be the fx curve for the situation. So now all we have to do is find the area under this curve. So because we can define dw as f dot ds, right? Integral f dot ds will give us the total work done by the force f. And integral f dot ds is nothing but the area under the force versus displacement curve. So the answer comes out to be 5250 joules, which would be option D. So moving on to problem number 2. So we have a block that is slipping down from a point B on an inclined plane AB, which is making an angle theta with the horizontal. The region BC is smooth and the remaining section is rough, coefficient of friction being mu. It is found that the block comes to rest exactly when it reaches a point A, and it's given that BC equals twice of AC. So if I call the distance AC as x, BC would be 2x. So we have to find this relationship between mu and tan theta. I mean, as we know, the block initially starts from rest and it finally comes to rest. We can simply use the work energy theorem, right? So it states that the work done by all the forces acting on the body equals to the change in kinetic energy produced in the body. The body starts from rest and comes to rest, which means the change in kinetic energy would be 0. The forces acting on this body B is, first of all, the normal force, then we have the force of gravity, and then we have kinetic friction acting on it. So the normal will not do any work because the displacement vector and the normal are perpendicular to each other. The work done by mg multiplied by displacement in the direction of mg, which will be this height h, and the work done by kinetic friction will start acting only when the block reaches C, and from this point kinetic friction will start to act and its magnitude will be F multiplied by x. So work done by normal would simply be 0. Work done by mg will be the force multiplied by the displacement. The displacement is this height, which is 3x sine theta. The work done by friction will be the magnitude of friction is constant, which is mu times the normal reaction, and the normal reaction on the block is mg cos theta, and the displacement of the block is only this much, right, which is x. As friction acts only along AC, it will be x, and this should all add up to 0, and from here you can see, and from here mu comes out to be 3 tan theta. So answer would be 3. So this is problem number 3. So we are given a force which varies with position, and we have to find the work done by this force in moving a particle from point A to point B along this line segment. Okay, so the displacement vector will be dx I cap plus dy j cap in Cartesian coordinates. And so the work would be integral of, so if you do the dot product of the force and displacement vector, you'll get minus x dx y dy. So the limits are for the x limits will be from 1 to 0 and the y limits will be from 0 to 1, and if you solve it, you'll get the answer as 1 joules. So in this question, a platform is moving up with an acceleration of g by 2, and we have to find the work done by the normal reaction on this block. So the work done by any force, again, it's defined as the dot product of the force with the displacement of the point of application of the force. In this particular case, first let's draw the FBD of the block. So we have a normal reaction, we have the weight of the block, and the block is moving up with an acceleration of g by 2. So now we can write F equal to ma for the block, and we'll get the normal reaction as 3 by 2. Oh yeah, and by the way, you guys have to keep one thing in mind. They are asking the work done by normal reaction on the block with respect to a person standing on the ground frame. If the guy was standing over here, then with respect to this guy, the work done by normal on the block will be 0 because with respect to this guy, block's displacement in the vertical direction is 0. So the work done by normal will be 0. But in this problem, we have to find the work from the ground frame. Okay. So now what is the work done by normal? So let's say after some time, this point displaces up by an amount of s, right? So we can easily say the work done by normal will be n times s because the angle between force and displacement vector is 0. So we can simply say it's n multiplied by s. So if we can somehow find the value of s, then our question is done. And s we can easily find using kinematics because we know the acceleration of the platform. So the s as a function of time will be half g by 2 t square. So now all we have to do is substitute, and we'll get the answer as 3 by 8 g square t square. So option D will be the answer. Okay, so moving on to the next problem. So in this question, we have been given a force which is initially a scary expression, but we can simplify it to a large extent. And the particle is given to be taken from the point a comma 0 to 0 comma a in along a circular path, okay, of radius a about the origin in the xy plane. So let's first of all draw a diagram. So it's taken from point a comma 0 to 0 comma a along a circular path. So the displacement vectors will be along this circle, okay, all the time. Let's say we take a general point on this path whose coordinates is x comma y, and let's say the position vector is represented by r vector. So we can clearly say r vector equals x I cap plus y j cap. And also as we know this, all such x comma y lies on a circle, we can say x square plus y square equals a square. Now in the force expression, there is an x square plus y square. So we can substitute that as it is a constant, we can take it out. So the force expression becomes k divided by a cube times x I cap plus y j cap. Now clearly this is the position vector of the particle r. So we can simply replace it with r, and the force expression simplifies as this. And from this equation, we can see that the direction of force is radially outwards, which means it's in this direction. And clearly the displacement vectors are tangential to the path, right? So at each point, if you do the dot product of f dot ds, it will come out to be 0 because the force is radially outward and the displacement vectors are tangential. So, and hence the answer to this problem will be 0. Moving on to the next problem. This question claims that W1, W2, W3 are the work done in moving a particle from point A to point B along 3 different paths in the gravitational field of a point mass m. So we have to find the correct relation between W1, W2 and W3. So let's say if we have a mass m1 that is fixed and we have another mass m2 which we have to move from a point A to a point B. Okay, so all we have to do is find the potential due to mass m1 at point A and the potential due to mass m1 at point B. So the work done in moving this particle m2 from point A to point B will be mass m2 multiplied by the potential at point B minus the potential at point A. So this would be the work done in moving a. And if I want to write the potential due to this mass m at a radial distance of r, it's going to be minus gm1 divided by r. So the key observation is that the potential only depends on this radial distance. So, and if we observe the mass m here, the radial distance of point A and the radial distance of point B is, let's say, r1 and r2. So the work done in moving a particle from A to B using this result depends on the delta V, and delta V is constant irrespective of the path taken. Option B will be the answer. You could have also made the argument that as it is a conservative force, as the gravitational force is a conservative force, the work done along all the paths is same, but I just want to prove this. So yeah, option B will be the answer. So we have a force that is minus k times y I cap plus x j cap. So this time it's not position vector, okay? And we are starting at the origin and the particle is taken along the positive x-axis to a point a comma 0 and then parallel to the y-axis to the point a comma a. The total work done by the force F on the particle is. So we start from the origin and we go till point a comma 0 along the x-axis, and then we go parallel to the y-axis to the point a comma a. So we have to find the work done. Let's name these points 1, 2 and 3. So the work done from 1 to 3 would simply be work done by 1 to 2 added with work done by 2 to 3. So now work done from 1 to 3 will be integral of the force vector, which is minus k y I cap plus x j cap, dotted with the displacement vector. So in this case, the displacement vector will be dx only. So this will be dx I cap, and the dot product and the limits will be from, so as you can see, the y term there is no component in the y. So as you can see, the limits will be from 0 comma 0 to a comma 0. And the second integral, which is work done from 2 to 3, that will be the force F, which is yi cap plus xj cap, dotted with the displacement vector, which is dy j cap in this case. And the limits will be from a comma 0 to a comma a. So after solving this integral, you'll get the answer as minus ka squared. We have a uniform chain of length L and mass m that is lying on a smooth table, and 1/3 of the length is hanging vertically down over the edge of the table. Okay, so the situation is something like this. This length is L by 3. So we have to find the work required to pull the hanging part onto the table. So if we use Newton's laws of motion, this is going to be a painful process. So instead, we'll just use energy conservation here. So the work done by the external agent who's going to pull this rope plus the work done by gravity. The normal won't do any work in this case, and we don't really have any friction in this case. This would be equal to the change in kinetic energy. So in this problem, the question actually was to find the minimum work that the agent had to do to pull this rope onto the table. So if we are talking about the minimum case, then we have to assume that we are doing the process so slowly that the change in kinetic energy of the block chain would be 0. So from here, the work done by external agent would be negative of the work done by mg, and negative of the work done by mg, we can just write it as a change in potential energy associated with the chain. So let's assume that this horizontal level of the table is the 0 potential energy level. So let's write the initial potential energy of the chain. So the potential energy of this part of the chain would be 0, and the potential energy due to this part of the chain. So the initial potential energy is the mass of this part. Now, as this is 1/3 of the length, this is going to be 1/3 the mass. Now, as this length is L by 3, the center of mass will be at a distance of L by 6, right? So this would become L by 6. Now, finally, this entire chain is on the table. So the final potential energy would simply be 0. Oh yeah, and there was this minus sign over here, which we forgot. So the work done by the external agent in order to pull the whole chain onto the table must be greater than or equal to mgl divided by 18, which would be option D. So we have a light inextensible string that goes over a smooth pulley as shown in the figure. It connects two blocks. Find the work done by the string on the block of mass 0.36 kg during the first second after the system is released from rest. Okay, so the problem is quite straightforward. So let's just say this mass is m, and let's just say this is 2m. So the acceleration of the system, so the weight of this block is 2 mg, and the weight of this block is going to be mg. So the net force along the string will be mg downwards, right? So the acceleration would be mg divided by the total mass of the system, which is 3m. That would be g by 3. Both these blocks are moving with an acceleration of g by 3. So in 1 second, what will be the displacement of the small block? So in 1 second, we can easily find the displacement of the block m using kinematics. It will be half g by 3 times t squared. So this comes out to be g by 6 meters. So we have to find the work done by the tension. If you draw the FBD of mass m, there will be tension, there will be mg, and the block is moving up with an acceleration of g by 3. So from here we can get the tension as 4 mg by 3. So the work done will be 4 mg by 3 g by 6, which is the displacement. So this will be 8 joules. So we have covered almost all the important cases in the syllabus for work calculation, and this would be the last problem of the day. So this problem came in Advanced 2019. So we have a particle. So it's moved along this path, okay, as specified by the arrows, and the force is given to be varying with the position, and we have to determine the work done on the particle by this force F. And again, we have to separately find out the works along these paths individually. So first, the work done along path AB. Now clearly along path AB, as the displacement is along the x direction, so the y component of the force is of no use to us, just forget about it. The work done will be integral alpha y dx. Now we have two variables in it, so we have to eliminate one. As we can observe, this y value for the line AB is constant and it is equal to 1. So we can substitute y for 1, and this simply comes out to be alpha dx, which would be alpha, because integral dx would be 1, right? 0 to 1, because the limits will be from 0 to 1. Now the work done along path BC would similarly only depend on the y component, which is 2 alpha x dy, and the x component here is constant and is equal to 1. Get rid of this. So this comes out to be 2 alpha. Final limit for y is 0.5 and initial limit is 1. So integral dy would be minus 0.5 and this should be minus alpha. Now work done along the path CD will be alpha y, and the y value is 0.5 dx. So this comes out to be, now integral dx will be, final limit is 0.5, initial limit is 1, so this will be minus 0.5, and this comes out to be alpha by 4. Now work done along path DE will be 2 alpha x will be 0.5 in this case, times integral dy. So this comes out to be alpha multiplied by, the limits of dy will be 0 minus 0.5, which is minus 0.5, minus alpha by 2. And this would be minus alpha by 4 actually. So, and also now the work done from E to F is going to be, displacement is along the x direction. So this would be integral alpha y dy. This would be alpha y dx. Now clearly the y value at this point for this path is 0. So the work done will be 0 in this case. And finally the work done from this will also be 0 because the x coordinate is 0. So our final answer minus 3 alpha by 4, which would be 3 by 4 joules. So that was it for this video, guys. That was it for this video, guys. Please like and subscribe if you enjoyed the session, and I'll be bringing more videos similar to this, covering all the important previous year problems. That's it. Thanks for watching, guys.